Two quick things before we start this lecture. Number one, proof of irrationality is not in class 9 syllabus. In last lecture, I talked about how we cannot represent root 2 in terms of p by q. And I did a procedure of first assuming that root 2 is a rational number. That is, I first assumed that root 2 is a rational number, and then I did a series of steps, and then I proved that we cannot represent root 2 as a rational number. So this is the proof of irrationality, and this is not in class 9 syllabus. I did this proof only for all of you to have a very clear understanding on why we have numbers like root 2, root 3 not being a rational number. And second thing, I said that we can predict how a rational number, when represented in terms of a decimal number, will end up being a terminating or a non-terminating repeating by looking at the prime factorization of its denominator. That is, we prime factorize the denominator and we look at the factors. So if it includes only 2 or 5 or 2 and 5, then it will be a terminating decimal. And if it contains a prime number other than 2 or 5 in its prime factorization, then it will be a non-terminating repeating. Again, this is also not in the class 9 syllabus, but it is good to know why or how we can predict a rational number becoming a terminating or non-terminating decimal based on its denominator's behavior. So keep this in mind. We move forward. We continue from where we left last lecture. So now what do we call these numbers or decimal numbers which are non-terminating and non-repeating? We call them as irrational numbers, or we can say that any number s or a number s is called irrational if it cannot be written in the fractional form p by q, where p and q are integers and q not equal to 0. This is what we just tried ourselves for the value of root 2 equal to 1.414, right? We have a number s that is 1.414 and so on, and we were trying to convert it into a fractional form p by q and we couldn't do it. So this is what it means. A number s is called irrational if it cannot be written in the fractional form p by q. And there are infinitely many irrational numbers. And one more thing that you might have observed is that square root of a prime number is always irrational. So whatever examples till now I have shown, all were square root of a prime number and all are irrational. So if I have to, or if you have to, just like that, give an example for an irrational number, all you have to do is that you have to take a square root of any prime number that will be a irrational number. We now go back to the types of numbers. Probably the very first lecture where we talked about different types of numbers. Anyway, I will do a quick revisit. We learned about natural numbers. Then we included 0 and we got whole numbers. So whole numbers are natural numbers plus 0. Then we had integers, that is all negative numbers also. And then we also had fractions, and together we call it as rational numbers. Okay. And now we have learned about irrational numbers. So I can summarize all rational numbers within this particular box. And I have irrational numbers like root 2, root 17, and further examples are pi and more, which all of you will learn in the subsequent time. And if I combine the rational numbers and irrational numbers, what I get is the real numbers. Okay, so all rational numbers plus all the irrational numbers, we will get real numbers. What is meant by irrational? As I said before, it means there is no logic to it. In the same way that if I express root 17 as a decimal number, it will be non-terminating and non-repeating, which is kind of not logically sensible for many people. So the collection of all rational numbers and irrational numbers is called real numbers, and we represent it with the letter R. So a real number is either rational or irrational. So whatever types of number that we have studied till now will always be a real number, The only thing will be it can be either a rational number or a irrational number. And on a number line, you take any real number, okay, you think of any real number, we can always find a point, a unique point on the number line to represent it. Like for example, we learned about root 2 equal to 1.414 and so on. Root 2 is a irrational number. That means root 2 is a real number. And what I'm telling you is that this particular value of root 2 can be represented on the number line and it will be a unique point. You may be now thinking, how do I represent root 2 on a number line or 1.41 so on a number line? We will learn it. Every unique point on the number line represents a unique real number. So we have the number line, you randomly select any particular point and that point will represent a unique real number. That unique real number may be a rational number or an irrational number, that we do not know. We have to see how it behaves, but it will always be a unique real number. Now we can come back to the very first questions that we asked, that is, can you think of a number that cannot be written as a simple fraction? The answer is yes, right? And what do we call those numbers? We call them as irrational numbers. Okay, now can you find an example in nature or daily life? Actually, there are so many of them, and as I said at the very first, it is there even inside this pyramids. We now start with how to locate irrational numbers on the number line, starting with root 2. Let us first consider a triangle OAB. So by now, all of you will be familiar that we can consider a triangle, okay, OAB with the base and height of 1 unit in length. So the base is going to be OA with 1 unit in length and the height AB again 1 unit in length. Now what will be the hypotenuse OB? We can write using Pythagoras theorem that OB square is equal to OA square plus AB square. This is nothing but 1 square plus 1 square, or OB square is equal to 2, or OB is equal to root 2. We only consider the positive square root values, okay. Now the question is that how do we represent numbers like root 2 on a number line? So let us draw a number line. Consider this number line. I have not made any numbers on it. We will do that. When you learn mathematics in class 9, we are not actually emphasizing the type of unit. That is, we do not say whether it is 1 meter in length or 1 centimeter in length or 1 kilometer in length. The type of unit is not discussed in class 9 mathematics, and for that reason we will represent each length as a unit. And so we define each of this gap to be 1 unit in length, okay. And now we have to locate root 2 unit on the number line. Let me first denote numbers on the number line, and that can be, as I said before, each of this gap is going to be 1 unit in length, and we have to locate root 2 unit on the number line. So it's simple. What we do to locate root 2, what we do is that we will first plot a right angled triangle OAB on the number line, and then we will make use of the length of the hypotenuse to construct the root 2 on the number line. So first of all, I will take the 0 to 1 distance, which is going to be 1 unit as the base, and for the height I will again construct a perpendicular line of 1 unit in length. Then I can join it. I will get a right angle triangle. So distance is going to be root 2 in length. First, let me construct the right angled triangle. So I put the scale 0 to 1. I construct the base. Now I will construct the height. Again 1 unit in length. Now I will join to get the hypotenuse. Now I have a right angled triangle of 1 unit of base, again 1 unit of height, and this hypotenuse will be root 2 in length. Now it's simple. You take your compass, okay, you put your pointed arrow here and the pencil at this particular position, and what we do from here, we just rotate the compass and get the position on the number line, and that distance will be root 2. I will do that now. So now I have just plotted the root 2 position on the number line using a compass, and this particular distance will be square root of 2. Let us move forward. Example number 4. Locate root 3 on the number line. Again, I'll start with the number line, and as I said before, each of these gaps will be 1 unit in width, so it is equivalent everywhere. And let us now denote root 3 on the number line. Now the underlying problem that we have to figure out is that we have to construct a right angled triangle of hypotenuse equal to root 3. So now I will only denote the point 0 on the number line. So this is going to be 1, 2, 3, 4 and so on, and this will be minus 1, minus 2. I'm not denoting these numbers for now. If we look back on how we plotted root 2, we can see that we have a right angled triangle with the hypotenuse as root 2. Now what I can do, I can continue further taking this particular thing as the base. I'll further construct another vertical line of length 1 unit, and this new hypotenuse will be the value of root 3. This is what I'm going to do here. Okay, so I start with the first right angle triangle that we constructed of base and height equal to 1 unit in length to get a hypotenuse of root 2. Let's do that. I have the base now. I will construct a vertical line again of length 1 unit. I have the height of 1 unit in length. Now I will construct the hypotenuse. Now I have the hypotenuse of length root 2. Okay, so this is going to be OAB, and OB will be equal to root 2. Now what I will do is that I'll take OB as the base of length root 2 unit, and I will construct a line perpendicular to OB of length 1 unit in size. Let me do that. So from OB perpendicular to OB, I construct a line which is 1 unit in length. I will denote this new endpoint as C. Now I will join OC. Now what will be the length of OC? If I look at this particular right angle triangle, that is OBC, from triangle OBC I can write OC square is equal to OB square plus BC square. Now what is the length of OB? OB will be root 2 square plus BC is 1 unit, so 1 square. This is going to be 2 plus 1, or OC square is going to be 3, implies the value of OC will be root 3. So we have now constructed a line of length root 3 in size, which is this OC. Now the same way, I take the compass, I put the pointed head on this particular position, I put my pencil at this particular position, and then I will rotate. I will get root 3 on the number line. Let me do that. So I have constructed this particular curve, and this new point I will denote as D. So this is going to be D. and this length OD will be equal to root 3. OC will be equal to OD and this will be equal to root 3 unit in size, and just like that we have located the length root 3 on the number line. So what have we done here? To plot root 3, we first plotted root 2, right? What we did, we first plotted root 2, we got OB value as root 2, then using that we constructed a second right angle triangle to get our required value of root 3. So what have we done here? We wanted to plot root 3, and to do this we have to first plot the root 2. Imagine we have to locate root 5. How we will do this? First we will plot root 4, before that we will plot root 3, before that we will plot root 2. Okay, so we plot root 2, then we get root 3, then we get root 4, and then we will get root 5. This is the way we are going to do. But there are some loopholes or things that we can tweak to make our life easier. Okay, but let me summarize. So this is the summary. To locate root n, that is for any positive integer n on the number line, we will have to first locate root n minus 1. We will do an additional example. Let us locate root 2 on the number line. How do we do that? To locate root 7, we will have to locate root 6, and before that we will have to do root 5, and before that root 4 up till root 2. Let's do that. I will take the starting point of root 3 that we have constructed before. To locate root 7, what do we have to do? First we have to plot root 6, before that we have to plot root 5, before that root 4, before that root 3, and before that root 2. So we have already plotted root 3 on the number line, and I will start from the previous example. Okay, so OC length is going to be root 3, and now I will construct more triangles, that is more right angle triangles, to get the value of root 7. Just a quick recap, I have OC equal to root 3 and BC equal to 1. Now what I will do, I will construct a line perpendicular to OC of length 1 unit in size, and then I will join to get the hypotenuse, and that hypotenuse will be the value of root 4. Let me do that. Let me denote the new point as E. So what will be the length OE? OE will be equal to, I can write OE will be equal to square root of OC square plus CE square. And what is the value of OC? OC is root 3. So OC square will be 3 and CE value is 1. So together I have OE going to be root 4. So now I have OE equal to root 4. Now I will proceed to calculate root 5. Again what I will do, I will construct a line perpendicular to OE of length 1 unit, and then I will join this to get root 5. Let me do that. Let me denote the new point as F. Now what is the value of OF? Let us calculate. We will make use of the triangle OEF. OF will be equal to square root of OE square plus EF square, and that is nothing but OE square is nothing but root 4 or 4 plus EF square is nothing but 1, implies OF is going to be root 5. Now I have to get root 6. How do we do it? I will construct a line of 1 unit in size perpendicular to OF, and then I will join this. I will get root 6. Let me do that. I'll denote the new point as G. What will be the value of OG? I can write OG is equal to square root of OF square plus FG square, and the value of OF is root 5, so OF square will be 5, and FG is 1, so FG square will be again 1, implies OG is root 6. And the final step, locating root 7, again I will plot a line 1 unit in length perpendicular to OG, and then I will join this. I will get root 7. Let me denote the new point as H. What will be the value of OH? OH will be the root 7 that we want. How do we locate it on the number line? We take a compass, we put the pointed head here, and we take the pencil at this point, and then we just rotate it. You will get the value. Now I will make the plot. Okay, it will be an approximate one because I am doing it digitally, but when you do it on pen and paper you will get the exact value. Okay, again reminding you, this is going to be an approximate value because I am doing digitally. I have not been very exact at this joining of points, but when you do it on paper you will get the correct or the exact point. Let me do that. So I have approximately drawn a complete circle, okay, of radius OH, which is nothing but root 7. Okay, so what I have done is that I have drawn a circle of radius OH, and this OH value is nothing but root 7. Okay, and this intersection point will be the point root 7 on the number line. Okay, I can denote this point as P. So OP will be equal to root 7. Imagine we have to plot root 9. How do we do that? We continue the process. First I draw 1 unit length perpendicular to OH. I join, I get the hypotenuse, that will be root 8. Again I'll continue, I'll get root 9, and then again I can draw a new circle, and that will be root 9 on the number line. Now if I join all these points, okay, what I will end up is that I will end up into a open curve which is continuously increasing. In this particular problem, when we have to locate root 7, do we have to do all these small triangles, or can we do it in a much faster way? Let us look at it. So let us look at a alternate way to plot root 7 with smaller steps. What I would do is this. Observe. So I have 0 point here, 1 and 2. Now the trick I do is that instead of starting from a right angle triangle of base 1 and height 1, I will first plot a right angle triangle of base 2 and height 1. See, first I will construct the base of length 2 unit, then I will construct a height 1 unit, I will join the hypotenuse, I will get this hypotenuse as length root 5. Why? The base is 2 unit, the height is 1 unit, So what will be the value of this hypotenuse? It will be, let's say I name this right angle triangle as OAB. Okay. OB will be equal to square root of OA square plus AB square, and value of OA is nothing but 2 unit, and OA square will be 4 plus AB square will be 1, and together OB will be root 5. So instead of plotting root 2, then root 3, then root 4, then root 5, I directly jump to plot root 5 with the triangle. Now it is simple. What I can do, I will plot again 1 unit, I will get root 6. I will plot 1 unit, I will get root 7. And then I can directly make the cut. So this is a much faster way. Instead of plotting all the small triangles, I directly start from a different right angle triangle with the base 2 in unit and 1 unit in height. Together I get a hypotenuse of root 5. Let me do that. I made the second right angle triangle with the base root 5 and height 1 unit. So this particular distance will be root 6. I'll continue. Let me note these points. This can be C and this will be D. Okay. Now the value of OD will be simply root 7. Now all I have to do is I have to take the compass, put the pointed head here, put my pencil end here, draw the curve, get the value on the number line. If I do that, and I will get approximately like this. And let me note the new point as P. So the value of OP will be same as value of OD, as same as root 7. So now you see I constructed root 7 length much faster than the previous method. Now how do we construct root 9? Let's say we have to construct root 9. How can we do? Much easier, right? Root 9 is nothing but 3. Let's say we have to plot root 11. How do we do that? Let's say you are going to proceed the original way, that is making small triangles. It will be a very long process. You can start with the base of length 3 unit, 1 unit in height, join, you will get root 10. This will be root 10. Again make 1 more unit in height, join this, and you will get root 11. You have to join, draw using compass, and you will get root 11 on the number line. So in this way any large numbers can be plotted. Once more, let us say we have to plot root 11. How do we do it? If we are going to plot using the small triangles, it will be a very long process. Instead, what you can do is that you can start from a triangle with the base 3 units in length and a height 1 unit. Join, you will get a hypotenuse of root 10. Again you make 1 more unit, 1 more line of length 1 unit, join, you will get root 11. Then using compass you can extend to get the point on the number line. So in this way any value you want to plot, you can do it much faster. So any large number we have to plot, the basic principle is that start with the closest square value. To plot root 5, I use the closest square value 4. Okay. To plot root 9, it is nothing but 3, so there is not a problem. To plot root 11, I again take the closest square value, that is 9, and then I make the plot. So imagine we have to plot, let's say, root 145. How do we do it? Take 144, which is the closest square root, and the square root value will be nothing but 12. So take 12 as the base, 1 unit in height, join, how much you will get? 12 square plus 1 square will be 145, square root of 145, and you can easily plot it on the number line.